43, we have a cross-section along a diameter of a long cylindrical conductor of radius 2 centimeters, carrying a uniform current of 170 amps. What's the magnitude of the current's magnetic field at a radial distance of 0, 1, 2, and 4 centimeters? All right, so we're basically just going to be using Ampere's law. We'll be drawing our beautiful Amperian loops coaxial with the center of the cable. So the first one, when we're at 0 meters away from the center, and this one's kind of hard to even visualize, but if you're 0 meters, it means you're basically just at this point. How much current is traveling through that point? The answer is 0. So the enclosed current is 0, no matter what or how you do ds. And I know some of you are like, wait, 0 divided by 0? Yeah. But basically, the magnetic field must be 0. Where it gets a little bit more interesting is at 1 centimeter. So at 1 centimeter, we're halfway out to the outside edge. And the question is, what current is passing through that red shaded area? Well, to figure that out, we know 170 amps is passing through the entire wire. To figure out what fraction of that 170 amps is flowing through the red shaded area, we simply have to set up a fraction, where this top, the numerator, is the area of this red area, and the bottom is the area of the entire wire. Again, remember the radius of the wire is 2 centimeters, and we're currently at 1 centimeter. So there's our 1 centimeter, 2 centimeters, just pi r squared times the 170. Our ds now is going to be the circumference of this loop right here. So that's going to be 2 pi times the radius, which in this case is 1 centimeter. So back here again. Solving that, you'll discover the magnetic field at that distance is about 8.5 times 10 to the minus 4 Teslas. See, what's the magnetic field at the outside of this thing? Well, at that point, we actually have a really nice situation. At the outside edge here, the total current enclosed inside of this is all of the current. And so this actually works out fairly nicely. If you think about this as our Amperian loop, forgive my drawing, it's all the current, and the circumference is just going to be 2 pi r, or in this case, the radius is 2 centimeters. If you solve that, you get that. Finally, what about at 4 centimeters? So now we're outside of the wire itself. Pretend I can draw my Amperian loop all the way around here. What's going to happen? Well, my Amperian loop still encloses all of the current, so all 170 amps. But my ds is going to be the circumference of this new Amperian loop, which is going to be 2 pi times 0.04 meters. And if you solve this one, it's the exact same answer as B. It drops by a factor of 4 from what we were, or actually in this case, a factor of 2 from what we were there. Yeah, ironically, it's the exact same answer. Hopefully, this helps. Good luck.